Hello students, today we are going to see the topic the matrix of linear transformation. The matrix of linear transformation. In this section, we see that every linear transformation T from Rn to Rn is actually a matrix transformation. Matrix transformation x bar to A into x bar, and the important properties of T are intimately related to familiar properties of matrix A. Okay. Let Rn be n by n identity matrix. Identity matrix. We denote the columns. We denote the columns of A from left to right, by E1 bar, E2 bar, and so on up to En bar, where E1 bar is equals to matrix 1 0 0 and so on up to 0, and dimension of this matrix is n by 1 because this matrix contains n number of rows and only one column. E2 bar is equals to matrix 0 1 0 and so on up to 0. Dimension of this matrix is also n by 1, and so on up to En bar is equals to matrix 0 0 and so on up to 1. Dimension of this matrix is n by 1. By definition of scalar multiplication for any x bar is equals to x1, x2 and so on up to xn in Rn, we have x bar is equals to matrix x1, x2 and so on up to xn is equals to x1 into E1 bar plus x2 into E2 bar plus and so on up to xn into En bar. This shows that every vector in Rn is a linear combination of E1 bar, E2 bar, E3 bar and so on up to En bar. This shows that every vector in Rn is a linear combination of vector E1 bar, E2 bar, E3 bar and so on up to En bar. Let T from Rn to Rn be a linear transformation. call this equation number star. Apply T on both sides of equation star. We get T of x bar is equals to T of x1 into E1 bar plus x2 into E2 bar plus and so on up to plus xn into En bar, okay, which is equals to x1 into T of E1 bar plus x2 into T of E2 bar plus and so on up to xn into T of En bar by definition of linear transformation, which is equals to, this can be written as matrix T of E1 bar, T of E2 bar and so on up to T of En bar into matrix x1, x2 and so on up to xn, which is equals to A into x bar, where A is equals to matrix T of E1 bar, T of E2 bar and so on up to T of En bar. Okay. Clearly, this matrix is of dimension m by n. Clearly, A is m by n matrix. Let us write down one theorem. Let T from Rn to Rn be a linear transformation. Be a linear transformation. Then there exists a unique matrix. There exists a unique matrix A such that P of x bar is equals to A into x bar for all x bar in Rn. For all x bar in Rn. Okay. And this A matrix is called standard matrix for the linear transformation T. Let us take one note. The matrix A in the above theorem is called the standard matrix for linear transformation T. For linear transformation where A is nothing but matrix T of E1 bar, T of E2 bar and so on up to T of En bar. Let us take some examples. First example is find the standard matrix A for the dilation transformation T of x bar is equals to 3/2 into x bar for x bar in R2. Let us see solution. See here, x bar in R2 and your linear transformation is applied on x bar. So domain for linear transformation is R2 whose dimension is 2. Here we require two standard bases, E1 bar and E2 bar. We have T of E1 bar is equals to T of, for our 2 E1 bar is 1 0 which is equals to, here linear transformation is T of x bar is equals to 3/2 into x bar. So here is 3/2 into x bar means 3/2 into matrix 1 0 which is nothing but 3/2 0. Okay. E2 T of E2 bar is equals to T of 0 1 which is equals to 3/2 into 0 1 which is equals to 0 3/2. Okay. Therefore standard matrix A is equals to T of E1 bar T of E2 bar which is equals to 3/2 0 0 3/2. This is the standard matrix for this linear transformation. Okay. Let us take next example. Second, find the standard matrix. Find the standard matrix of T where T is a linear transformation T from R3 to R2. Okay. T of E1 bar is equals to 1 3. T of E2 bar is equals to vector 4 minus 7. T of E3 bar is equals to vector minus 5 comma 4. Okay. Where E1 bar, E2 bar and E3 bar are columns of I3. Okay. Solution. Here we have T of E1 bar is equals to vector 1 comma 3. T of E2 bar is equals to vector 4 comma minus 7 and T of E3 bar is equals to vector minus 5 comma 4. We have to find standard matrix for linear transformation, and we know that standard matrix for linear transformation is matrix A is equals to T of E1 bar, T of E2 bar and T of E3 bar, which is equals to matrix 1 3. T of E1 bar is 1 3, T of E2 bar is vector 4 minus 7, T of E3 bar is minus 5 4. This is the standard matrix for given linear transformation. Let us take next example. Show that T is a linear transformation T is a linear transformation by finding a matrix that implements the mapping where first is T of x1, x2, x3 is equals to x1 minus 5x2 plus 4x3, x2 minus 6x3, and second one is T of x1, x2 is equal to 2x2 minus 3x1, x1 minus 4x2, 0, x2. Okay. We solve first part. Here we have to find standard matrix for the linear transformation. Okay. Here T of x bar. Here x bar, coordinate of x bar is 3. So T is a linear transformation from R3 to here. Coordinate of this vector is 2. So it is a linear transformation from R3 to R2. So here we require 3 columns of I3 matrix. T of E1 bar is equal to, what is E1 bar? T of E1 bar is 1 0 0, okay, which is equal to, here this is x1, x2, x3. What is linear transformation? T of x bar is equal to x1 minus 5x2 plus 4x3. So put these values in this vector, you will get x1 is 1, x2 is 0, x3 is 0. So here you will get only 1. Here x2, x3 is 0. So this value is 0. Okay. Similarly, calculate T of E2 bar, T of E3 bar. T of E2 bar is equals to T of 0 1 0, which is equals to, here x1 is 0 minus 5 into 1. So here is remains only minus 5. So you will get minus 5, 1. Okay. T of E3 bar is equals to T of 0 0 1, which is equals to, here x1 is 0, x2 is 0, plus 4 into 1. So here is 4. Here x2 is 0, minus 6 into 1 is minus 6. This is P of E3 bar. And we know that the standard matrix A is nothing but P of E1 bar, P of E2 bar into P of E3 bar, okay, which is equals to, what is T of E1 bar? T of E1 bar is 1 0. T of E2 bar is minus 5 1. T of E3 bar is 4 minus 6. This is the standard matrix for linear transformation. Now find standard matrix for next linear transformation. See here, coordinate of this vector is 2. So this is a linear transformation from R to 2. Here coordinate of this vector is 1 2 3. So this is R3. Here we require 2 columns of identity matrix I2. So T of E1 bar is equals to matrix T of 1 0, okay, which is nothing but T of 1 0, which is nothing but matrix minus 3 1, next is 0 0. T of E2 bar is equals to T of E2 bar is second column of matrix I2, which is 0 1, which is equals to, put these values in this vector. You will get here x1 is 0, x2 is 1, so here is 2. Next is x1 is 0 0 minus 4 into x2, so here is minus 4. Next entry is 0 and next entry is 1. We know that standard matrix is A is equals to matrix T of E1 bar, T of E2 bar, which is equals to matrix minus 3 1 0 0 2 minus 4 0 1. This is the standard matrix for given linear transformation. Let us take next example. Let T from R2 to R3 be a linear transformation such that P of x1 comma x2 is equals to x1 minus 2x2 comma minus x1 plus 3x2 comma 3x1 minus 2x2. Okay, find x bar such that T of x bar is equals to minus 1 comma 4 comma 9. Okay. Solution, we write given T in matrix notation as T of x1 x2 is equals to matrix, write this vector in matrix form x1 minus 2x2 minus x1 plus 3x2, 3x1 minus 2x2. Okay, this is nothing but 1 minus 2 minus 1, 3, 3 minus 2 into x1, x2. Okay, into x1, x2. We have to find x bar such that P of x bar is equals to vector minus 1, 4, 9. For this we have to solve P of x bar is equals to vector minus 1, 4, 9. Okay, that is we have to solve P of x bar is 1 minus 2 minus 1, 3, 3 minus 2 into x1, x2 is equals to matrix minus 1, 4, 9. Okay, consider the augmented matrix. Consider the augmented matrix and row reduce it. Augmented matrix is 1 minus 2 minus 1 minus 1, 3, 4, 3 minus 2, 9. Okay, its row reduced form is matrix 1 0 5 0 1 3 0 0 1. This is homework to you obtain this row reduced form of this matrix. Okay, from this matrix you will get x1 is equals to 5 and x2 is equals to 3. x1 is equals to 5 and x2 is equals to 3. Therefore, x bar is equals to matrix x1 is equals to x2, which is equals to x1 is 5 and x2 is equals to 3, is such that P of 5, 3 is equals to matrix minus 1, 4, 9. Okay. Okay. We will stop here. Thank you.